I'm Ralph Clayton, and today we are going into one of the most misunderstood ideas in modern physics: zero-point energy. It sounds like science fiction. It sounds like secret power. It sounds like the kind of phrase that belongs in a laboratory, a classified program, or a future civilization that has learned how to pull infinite energy out of empty space. But the real story is more interesting than the myth, because zero-point energy is real. It is not fantasy. It is not just a phrase from conspiracy forums or speculative engineering. It is a serious concept inside quantum mechanics and quantum field theory. It appears when we ask a simple question: what happens when a physical system reaches its lowest possible energy? In classical physics, the answer seems obvious. If you cool something down far enough, all motion should stop. The particles should become still. The vibrations should vanish. The system should reach perfect rest, absolute silence, zero energy. But quantum mechanics says no. Nature does not permit perfect stillness. Even at the lowest possible state, something remains. Not heat in the ordinary sense, not fuel, not a hidden battery, but a minimum quantum restlessness, a ground state energy, a floor beneath which the system cannot fall. That is zero-point energy. It is the hum beneath the silence, the motion that cannot be removed, the last remainder of quantum reality after every ordinary form of energy has been stripped away. And in 2026, this idea remains one of the strangest and most important concepts in physics. It matters in molecules. It matters in quantum fields. It matters in nanotechnology. It matters in cosmology. It may be connected to dark energy. It is involved in the Casimir effect. It appears in discussions of superconducting circuits, materials, vacuum fluctuations, quantum geometry, and the deep problem of why empty space does not behave the way our equations naively suggest. But it is also one of the most abused phrases in modern science culture. Because whenever people hear that the vacuum has energy, they ask the obvious question: can we use it? Can we extract it? Can we build a machine that runs on the energy of empty space? Can zero-point energy power the world? And this is where we need discipline, because the honest answer is not a Hollywood yes. It is also not a dismissive no that treats the subject as nonsense. The honest answer is more precise. Zero-point energy is real. Vacuum effects are real. Quantum ground states are real. Casimir forces are real. Modern research is still finding new ways that vacuum fluctuations and quantum geometry may appear in physical systems. But there is no verified zero-point energy generator. There is no proven free energy device. There is no demonstrated machine that extracts unlimited net power from the quantum vacuum. And if someone claims otherwise, the burden of proof is enormous. So today, we are going to separate the physics from the mythology. We are going to ask what zero-point energy actually is, why it exists, how it shows up, what the Casimir effect really tells us, why dark energy makes the whole subject even deeper, why the cosmological constant problem remains one of the greatest unsolved problems in theoretical physics, and why, even if zero-point energy does not give us free power, it still may reveal something profound about the structure of reality. Let's begin at the simplest place, a vibrating system. Imagine a tiny mass attached to a spring. In classical physics, the mass can sit perfectly still at the bottom of the potential. No motion, no vibration, no kinetic energy, no potential energy. The energy can be zero. Now shrink that system down into the quantum world. Make it an atom in a molecule, or an electromagnetic field mode, or any system that behaves like a quantum oscillator. Suddenly, the classical picture fails. The system cannot have both a perfectly fixed position and a perfectly fixed momentum. That is the uncertainty principle. If the particle were exactly at rest, exactly in one place, with exactly zero motion, it would violate the structure of quantum mechanics. So the lowest possible state is not zero. It is not motionless. It has a minimum energy. For the ideal quantum harmonic oscillator, that energy is 1/2 of each bar times omega. 1/2, not zero. That half is the famous residue, the irreducible ground state energy. It is not there because the system is hot. It is not there because someone added energy. It is there because quantum mechanics does not allow the classical idea of perfect rest. This is the first key to understanding zero-point energy. It is not an extra fuel tank. It is the floor of the system. It is the lowest allowed energy. You cannot normally drain energy from a floor because there is nowhere lower for the system to go. That is why zero-point energy is so tempting to imagine as a power source and so difficult to actually use. The energy is there, but it is not necessarily available. That distinction matters. Energy existing in a system is not the same as usable work. To get work, you need a difference, a gradient, a flow, a system that can move from one state to another while doing something useful. A ground state is already at the bottom of the hill. You do not get a water wheel to turn from a lake with no waterfall. You need height difference. You need motion between levels. You need access to a lower state. Zero-point energy is strange because it says the bottom is not zero. But it is still the bottom. This is why many free energy claims collapse at the same conceptual point. They confuse the existence of ground state energy with extractable energy. They say, Empty space has energy. Therefore, we can harvest it. But physics asks the next question. Harvest it into what? By what cycle? What changes? What resets? What energy must be paid to return the system to its starting state? Does the full accounting produce network? So far, no verified device has passed that test. But to understand why physicists still care, we need to move from particles and springs to fields. Because in modern physics, the universe is not made only of particles flying through empty space. It is made of fields. The electromagnetic field, the electron field, the quark fields, the Higgs field, and many others. Particles are excitations of these fields. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. But even when there are no particles, the fields are not simply nothing. They have ground states. They have quantum structure. They have fluctuations. The vacuum in quantum field theory is not empty in the everyday sense. It is the lowest energy state of all the fields. That sounds like emptiness. But quantum emptiness is not ordinary nothingness. It is not a dead void. It is more like a silent ocean whose surface can never become perfectly flat. Not waves in the ordinary sense, not usable turbulence, but a restless mathematical and physical structure. This is where the phrase vacuum fluctuations enters the story. The vacuum is not filled with little particles popping in and out in the cartoon way people sometimes describe it. That image can be useful as a metaphor, but it can also mislead. The deeper point is that quantum fields have fluctuations, even in their ground state. Those fluctuations can have measurable consequences when systems are arranged in the right way. And the most famous example is the Casimir effect. The Casimir effect is often described like this. Take two very clean, neutral, conducting plates. Place them extremely close together. At very small separations, the plates experience a tiny force. They are pulled together. Why? One common explanation says that the space between the plates allows only certain electromagnetic modes, while the space outside the plates allows a different set of modes. The vacuum energy inside and outside is not the same. That difference produces a force. The plates move. This is one of the classic examples used to show that the quantum vacuum is not just a philosophical idea. It has consequences. It can push, it can pull, it can act. But even here, we need nuance. Physicists do not all describe the Casimir effect in exactly the same conceptual language. Some frame it in terms of changes in zero-point energy. Some emphasize quantum, electromagnetic interactions between charges and currents in the materials. Some describe it as related to van der Waals forces in a relativistic quantum setting. The measurements are real. The force is real. The mathematical predictions work. But the interpretation can be more subtle than the popular version. That matters because people often say, the Casimir effect proves we can get energy from the vacuum. No. It proves that quantum effects associated with fields and boundaries can produce measurable forces. That is not the same thing as an infinite power source. If the plates come together, work can be extracted from that motion in principle. But if you want to run a cycle, you have to separate them again. You have to reset the system. And that costs energy. The full cycle does not give you free power. The Casimir effect is real physics. It is not a loophole in thermodynamics. Still, it is important. At the nanoscale, Casimir forces can matter in tiny devices. They can influence microelectromechanical systems. They can create unwanted sticking. They can become a design constraint. They can also become a probe of quantum and material properties. And in 2026, research on Casimir forces is still active, extending beyond the ideal textbook picture of two perfect metal plates. Scientists study structured materials, real surfaces, temperature effects, geometry, time-dependent media, topological systems, exotic phases, and quantum materials. The Casimir effect began as a strange prediction about the vacuum. Now it is part of a broader research landscape where quantum fluctuations, materials, geometry, and nanoscale engineering meet. This is one of the important updates for 2026. 0-point energy is not a solved curiosity placed in a museum. It remains active at the frontier, not as free energy, as precision physics, as quantum materials research, as nanoscale force measurement, as a probe of how fields and matter interact. A good example is recent theoretical work exploring how vacuum, electromagnetic fluctuations can induce additional zero-point energy in solids. In that kind of research, the focus is not on building a vacuum-powered generator. The focus is on understanding how quantum fluctuations interact with materials, circuits, and many body quantum geometry. One proposal in 2026 suggested that electromagnetic vacuum fluctuations could create a measurable force in certain superconducting circuit setups, connected to what the authors called a quantum geometric force. That is the kind of frontier where zero-point energy is taken seriously. It is careful. It is mathematical. It is experimental in ambition. It is not a claim of infinite power. It is a claim that quantum vacuum effects may give us a new way to probe hidden properties of matter. And this is an important distinction. Real frontier physics often sounds strange, but it is still disciplined. It makes limited claims. It defines conditions. It predicts measurable quantities. It accepts failure. It invites verification. Pseudoscience often does the opposite. It takes the strangeness of real physics and turns it into unlimited possibility. It says, because the vacuum has energy, anything can be powered. Because quantum mechanics is strange, any impossible device might work. Because scientists do not know everything, this machine must be real. That is not science. That is rhetoric. Real science lives in the exact boundary between imagination and constraint. 0-point energy sits right on that boundary because the concept is genuinely profound, but the constraints are severe. Now let's go to the largest scale, cosmology. If quantum fields have vacuum energy, does that energy gravitate? Does it affect the expansion of the universe? Could it be dark energy? This is where 0-point energy becomes part of one of the deepest puzzles in all of physics. We know the universe is expanding. We also know that the expansion is accelerating. The name we give to whatever is driving that acceleration is dark energy. Dark energy is not a substance we have bottled. It is not a particle we have detected directly. It is a name for the observed fact that the universe's expansion behaves as if some component with negative pressure is pushing cosmic expansion faster over time. The simplest model is the cosmological constant, a constant energy density of space itself. Vacuum energy seems like an obvious candidate. After all, if empty space has energy, maybe that energy is what drives cosmic acceleration. This idea is elegant. It is tempting. It may even be partly right. But then the numbers become catastrophic. When physicists estimate vacuum energy using quantum field theory in a naive way, the answer can be enormously larger than the observed dark energy density. Not slightly wrong, not 10 times too high, not 1,000 times too high, depending on the assumptions. The mismatch is described as tens, 60, or even around 120 orders of magnitude. That is not a normal error. That is one of the worst mismatches between theory and observation in science. This is the cosmological constant problem. It asks a brutal question. Why does empty space appear to have such a tiny but non-zero energy density? Why is it not enormous? Why is it not exactly zero? Why does the value seem tuned to a scale that allows galaxies, stars, planets, and observers to exist? We do not know. As of 2026, this remains unsolved. There are many ideas. Maybe dark energy is a true cosmological constant. Maybe it is a dynamic field, sometimes called quintessence. Maybe gravity behaves differently on cosmic scales. Maybe vacuum energy is cancelled by unknown physics. Maybe the solution requires quantum gravity. Maybe our understanding of vacuum energy is incomplete. Maybe the observed value is selected in a larger landscape of possible universes. None of these answers has closed the case. That is why 0-point energy is not only an engineering question. It is a cosmological question. It forces physics to confront the relationship between quantum theory and gravity. And that relationship is still unfinished. Quantum field theory works astonishingly well for particles and fields. General relativity works astonishingly well for gravity and space-time. But when vacuum energy enters gravity, something deep becomes unstable. The equations seem to say the vacuum should matter enormously. The universe says it matters only very slightly. The gap between those statements is a wound in modern physics, a silent wound, an elegant wound, a wound hidden under the phrase dark energy. This is one reason 0-point energy remains fascinating. It is not because we are secretly one equation, away from unlimited power. It is because it exposes a place where our best theories do not yet fit together. That is often where revolutions begin, not in the easy places, in the contradictions. Now, let's return to Earth, because for most people, the question is practical. Could 0-point energy ever become a technology? The careful answer is this: 0-point effects already matter technologically in certain contexts, not as power sources, but as forces, noise floors, limits, and quantum phenomena. In nanotechnology, Casimir forces can matter. In quantum optics, vacuum fluctuations matter. In superconducting circuits, ground state fluctuations are central. In precision measurement, quantum noise and vacuum states can set limits. In quantum information, engineered vacuum states and squeezed states can improve measurement sensitivity. In materials physics, 0-point motion can affect crystal properties, isotope effects, superconductivity, and molecular behavior. In chemistry, 0-point vibrational energy affects reaction energetics. So yes, 0-point energy is technologically relevant. But that does not mean vacuum batteries. This is like saying gravity is technologically relevant because bridges, rockets, satellites, tides, and hydroelectric dams depend on gravitational physics. That does not mean you can build a machine that gets unlimited energy from gravity without a falling mass, flowing water, orbital mechanics, or an energy gradient. Physics always asks for the cycle. Where does the usable work come from? What state changes? What must be reset? What is the full energy accounting? This is the question every 0-point energy device must answer, and verified devices have not answered it. If a machine claims to extract power from vacuum energy, it must show clear, repeatable, independently verified net energy output. It must rule out hidden inputs. It must obey measurement discipline. It must survive skeptical replication. It must produce more useful work than it consumes over a complete cycle. Until then, it is a claim, not a discovery. And extraordinary claims require extraordinary evidence. That phrase can feel tired, but here it is exactly right. Because if someone truly built a zero-point energy generator, it would be one of the greatest technological breakthroughs in human history. It would transform energy, economics, geopolitics, climate, industry, and civilization. It would also require a revision or deep extension of our current understanding of thermodynamics, quantum field theory, or both. That is not impossible in principle. Science has been revised before, but it is not something we accept because a device looks mysterious. We accept it when the evidence forces us. So far, the evidence has not forced us. Now, there is another concept that often gets mixed into this conversation. Virtual particles. People say the vacuum is full of virtual particles popping into existence and disappearing. This picture appears everywhere. It is vivid. It is memorable, but it can be misleading. Virtual particles are not tiny balls that borrow energy from the universe, live for a moment, and then vanish like sparks. They are mathematical features inside perturbative quantum field theory. They appear in calculations. They help describe interactions. They are not particles in the same way detectable electrons or photons are particles. Vacuum fluctuations are real in the sense that quantum fields have measurable ground, state behavior. But the cartoon of temporary particles can lead people to think the vacuum is a boiling soup of harvestable little objects. That is too crude. A better way to say it is this: the vacuum is the lowest energy state of fields, and that state has quantum correlations and fluctuations that can influence physical systems. This is less cinematic, but more accurate, and with zero-point energy, accuracy matters. Because sloppy language creates false promises. False promises create bad science. Bad science wastes time, money, and public trust. The real story is already strange enough. We do not need to exaggerate it. Now let's ask a more philosophical question. What does zero-point energy tell us about reality? It tells us that emptiness is not simple. It tells us that stillness is not absolute. It tells us that the classical imagination fails at the foundation. In everyday life, we divide the world into things and nothing, objects and empty space, matter and void, motion and rest. Quantum physics blurs those divisions. The vacuum is not ordinary nothing. Rest is not perfect stillness. A particle is not a tiny hard object with a definite position and velocity at all times. Energy levels are not continuous in the old classical sense. The universe has a grain, a structure, a flaw. Zero-point energy is one sign of that flaw. It is the refusal of nature to become perfectly flat. It is the reminder that the quantum world is not built from silence, but from possibility constrained by law. That phrase matters. Possibility constrained by law, because 0-point energy is not magic. It is not infinite freedom. It is not a loophole. It is the opposite. It is quantum possibility under strict rules. This is the pattern we see again and again in modern physics. The deeper reality becomes, the stranger it becomes. But it also becomes more constrained. Relativity breaks common sense, but imposes the speed of light. Quantum mechanics breaks classical determinism, but imposes uncertainty relations and probability amplitudes. Thermodynamics allows engines, but imposes entropy. Quantum field theory allows vacuum fluctuations, but does not automatically allow free work. The universe is not simple, but it is not arbitrary. That is the line between science and fantasy. Science accepts strangeness, but it demands structure. Now, in 2026, where does the serious frontier stand? First, 0-point energy remains basic quantum physics. It appears in the ground states of oscillators, molecules, fields, and materials. Second, vacuum fluctuations remain experimentally relevant. The Casimir effect and related phenomena continue to be studied in increasingly complex systems. Third, quantum materials and superconducting circuits are opening new ways to explore ground, state fluctuations, and field matter coupling. Fourth, cosmology still faces the dark energy problem. The relationship between vacuum energy, the cosmological constant, and cosmic acceleration remains unresolved. Fifth, no accepted 0-point energy power technology exists. That is the status. Real phenomenon, active research, deep mystery. No free energy machine. All 5 statements must be held together. If you drop the first 3, you become dismissive and miss real physics. If you drop the last 2, you fall into hype. The truth is in the tension. There is something real here, but not the thing many people want it to be. At least, not today. Let's make this concrete with a simple analogy. Imagine standing at the shore of the ocean. The surface is never perfectly still. Even when the wind is calm, tiny ripples remain. Now suppose someone says those ripples contain energy. They are right. Then suppose they say, therefore we can power a city from the irreducible ripples of the sea, without changing anything else. That does not follow. You need a mechanism. You need energy flow. You need a gradient. You need engineering. You need thermodynamics. You need accounting. The quantum vacuum is not the ocean, but the lesson carries. Presence of energy is not enough. Availability of work is the issue. And the universe is very strict about work. This is one of the hardest ideas for the public conversation around energy. People often ask, how much energy is out there? But engineers and physicists ask, how much usable energy can be extracted under real constraints? A hot rock has thermal energy. But if everything around it is the same temperature, it cannot run a heat engine. A battery has chemical energy because it contains a usable difference in electrochemical potential. A river can turn a turbine because water moves from high to low. A solar panel works because the sun provides a flux of photons from a hot source to a colder environment. Energy technology is not about energy existing. It is about controlled disequilibrium. 0-point energy is tricky because the vacuum is already the equilibrium state, the ground state, the bottom. That does not mean vacuum. Physics cannot do anything. It means the dream of simply tapping it, like oil under the ground, is the wrong picture. Now, could future physics discover new ways to exploit vacuum-related phenomena? Maybe. Science should not close the door on unknown unknowns. There may be exotic states, engineered quantum systems, dynamical Casimir effects, squeezed vacua, non-equilibrium quantum fields, boundary manipulations, quantum thermodynamic cycles, new materials, new gravitational physics. But the word exploit must be used carefully. Using vacuum-related effects is not the same as extracting unlimited energy from the vacuum. For example, the dynamical Casimir effect can produce real photons from the vacuum when boundary conditions change rapidly. That sounds like creation from nothing. But energy is supplied by the changing boundary. The input is not free. The vacuum mediates the effect, but the energy comes from the drive. This pattern appears often. The vacuum participates. It does not pay the bill. That sentence is worth remembering. The vacuum participates. It does not pay the bill. At least, not in any verified technology we have today. This is also why 0-point energy is so attractive for science fiction. It is real enough to sound plausible, mysterious enough to feel cosmic, misunderstood enough to invite speculation, and deep enough that even experts admit unresolved questions. A good science fiction writer can use it beautifully. A bad inventor can abuse it easily. The public needs enough literacy to tell the difference. So here is a practical guide. When someone talks about 0-point energy, ask which version they mean. Do they mean quantum ground, state energy? That is real. Do they mean vacuum fluctuations in quantum field theory? That is real, but technically subtle. Do they mean the Casimir effect? That is real and measurable. Do they mean dark energy? That is observationally real, but its physical nature is unknown. Do they mean a new theoretical proposal in quantum materials or superconducting circuits? That may be serious, but it needs careful evidence. Do they mean a device that powers itself from empty space? that is not established. Ask for independent replication. Ask for complete energy accounting. Ask for peer-reviewed measurements. Ask whether hidden inputs are ruled out. Ask whether the device can be tested by skeptics. Ask whether it works under controlled conditions. If the answers become vague, be cautious. Real physics can be difficult, but it does not need to hide from measurement. Now, let's talk about why the myth persists. Partly, it persists because people want clean energy. That desire is understandable. Human civilization needs abundant energy. Climate change is real. Energy poverty is real. Geopolitical energy dependence is real. The dream of a clean, limitless, compact power source is emotionally powerful. If someone says the vacuum itself can provide that power, people listen. But desire is not evidence. Another reason is that modern physics is genuinely strange. Quantum mechanics has made impossible sounding things real. Tunneling, entanglement, superposition, antimatter, semiconductors, MRI, atomic clocks, quantum computing. So when someone says, "Scientists once thought this was impossible too," they are using a real historical pattern. But the lesson of history is not that every impossible claim is true. The lesson is that strange claims become science when they produce precise predictions and survive experimental attack. Quantum mechanics did not win because it sounded mystical. It won because it worked. Again and again. With numbers. With experiments. With technologies. With failures corrected by better theory. 0-point power would need the same path. Not stories. Not secrecy. Not impressive language. Evidence. There is also a deeper psychological reason. 0-point energy feels like a symbol. It suggests that emptiness is full, that the universe hides abundance beneath appearance, that scarcity may be an illusion, that civilization is trapped only because it has not learned the right key. That is powerful mythology. But physics is not obligated to satisfy mythology. Sometimes the universe gives us hidden abundance. Sometimes it gives us hidden limits. Often, it gives us both. 0-point energy is like that. It reveals hidden richness in the vacuum and hidden limits on what we can extract. Both are true. Now let's imagine the future. What would progress look like over the next decade? Not fantasy progress. Realistic progress. We may see more precise Casimir measurements in complex materials and geometries. We may see vacuum fluctuation effects used as probes of quantum materials. We may see better superconducting circuit experiments that manipulate ground, state electromagnetic fields. We may see improved understanding of quantum, noise, and squeezed vacuum states in precision measurement. We may see quantum thermodynamics clarify what can and cannot be extracted from engineered ground. state systems. We may see cosmological observations constrain dark energy more tightly, especially whether it behaves like a constant or changes over time. We may see progress toward quantum gravity that reframes the cosmological constant problem. We may see theoretical breakthroughs that explain why vacuum energy gravitates so weakly, or why our calculations are asking the wrong question. That would be enormous. Even without free energy, understanding zero-point energy better could change fundamental physics. It could sharpen quantum field theory in materials. It could improve nanoscale engineering. It could improve quantum sensors. It could deepen our understanding of dark energy. It could help connect quantum theory and gravity. That is already worth pursuing. Science does not need every discovery to become a generator. Some discoveries are maps. Some are warnings. Some are constraints. Some reveal where our theories break. Zero-point energy may be all of these. Now, for a moment, let's return to that phrase, 0 point. It sounds like nothing. The point of zero, the origin, the absence of quantity. But in quantum physics, 0 point does not mean nothing is there. It means the lowest possible state still has structure. That is almost poetic. At the bottom of reality, there is not absolute stillness. There is lawful restlessness. At the foundation, there is not dead emptiness. There is a vacuum with rules. At the minimum, there is not a blank. There is a ground state. And that ground state has consequences. Maybe that is the real lesson. Modern science keeps teaching us that nothing is harder to understand than nothing. The empty space between stars is not simply empty. The silence of a cooled molecule is not completely silent. The lowest state of a quantum system is not classical rest. The cosmological constant is not an easy number. The vacuum is not a simple void. And yet, none of this gives us permission to believe everything. The mystery is real. So are the limits. That is the mature position. Wonder without gullibility. Skepticism without cynicism. Open-mindedness without abandoning evidence. That is how we should approach zero-point energy in 2026. Not as a miracle power source. Not as a joke. But as a serious window into quantum reality. One that tells us our universe has a deeper flaw than classical physics imagined. One that appears in molecules, fields, nanoscale forces, materials, and cosmology. One that may connect to the biggest question of all. Why does empty space behave the way it does? When we look into the vacuum, we are not looking into nothing. We are looking into the ground state of the world. And the ground state is not silent. It is quiet, but not silent. That difference is where the science begins. So the next time you hear the phrase zero-point energy, do not immediately Think of a secret machine. Think of a molecule that cannot stop vibrating. Think of two tiny plates feeling a force from the structure of the vacuum. Think of a superconducting circuit sensitive enough to probe ground state fluctuations. Think of dark energy pushing galaxies apart across cosmic time. Think of the unsolved gap between quantum theory and gravity. Think of a universe where even the lowest possible state is not nothing. That is the real mystery. Not free energy, deeper reality. And perhaps that is more powerful. Because technologies come and go. But a better understanding of the vacuum would change the foundation beneath all technologies. It would change the meaning of emptiness. It would change how we connect quantum fields to space-time. It would change how we think about the origin, fate, and structure of the cosmos. And it would remind us that the universe still has secrets hiding in the places we once called empty. This has been VTM Podcast, episode 15. I'm Ralph Clayton. Thank you for listening. And until next time, keep questioning the future before it becomes the present.